In this video, we are going to discuss about Class C amplifiers. So this comes under power amplifiers. Let us discuss the circuit diagram of Class C tuned amplifier. This is your AC input signal, and you have a capacitor followed by a resistor and a common emitter configuration transistor. So this is your tuned circuit which is employed at the load, and with the help of coupling we are taking the output at this resistance RL. This Class C amplifiers are used in the radio receiver of high frequency, because at low frequency the impedance, the capacitive impedance is larger, therefore the circuit becomes bulky. The inductance and the capacitance value becomes bulky at low frequency. So this Class C tuned amplifier is used for high frequency applications. Here instead of RC, that is collector resistance, I have used a tuned circuit. Okay, this LNC is called as a tuned circuit. So why it is not used for the audio amplification means the audio amplification it amplifies for a wide band of frequency equally well, and it doesn't permit the selection of a particular desired frequency while rejecting the all other frequency. Whereas in the with the help of a tuned circuit, that is for example a radio receiver, the application of this Class C tuned amplifier, it is able to pick and amplify the radio frequency of desired frequency, and it will discriminate all other frequency in order to get the desired output. And so therefore this resistive load is replaced by a parallel tuned circuit. Why it is called parallel tuned circuit means L, C are connected in parallel, and whose impedance is strongly which depends on the frequency. So the use of the tuned circuit in conjunction with the transistor, which makes possible selection and the efficient amplification of a particular desired radio frequency. So such an amplifier is called as a tuned amplifiers. Okay, so this is used as a tuned amplifiers, and I have already told it is used for high frequency applications, high frequency RF applications. And it is highly efficient because the efficiency, okay, the efficiency is more than 90%. Okay, so we know that the conversion efficiency formula is P AC divided by P DC. So you can see the amplification for the minimum input signal we get a maximum output. Okay, so it is highly efficient. Okay, it is more than 90%. So let us discuss the operation. Um, when the no for in order to determine the DC load line, the capacitor becomes open circuit, and this also open circuit, so the AC signal will not present, and this is your biasing resistor. Okay, this is your biasing resistor, and the capacitor is open circuited and the inductance is short circuited. So the basically the DC load line of this circuit is, I can write it as PDC, sorry, RDC is equal to DC resistance of the inductor. Okay, so let me draw the this is IC and this is VCE, and we know that the DC load line is like this, and this is your VCC by RDC, and this is nothing but VCC. Okay, so in order to determine the Q point, that is for AC load line, if we apply the AC load line, that is AC input signal, it is given to a clamp circuit. Okay, so this here you have a capacitor and followed by a resistor RB. Okay, so this is your input signal. Let me assume this is of Vm and this is of minus Vm, and it is connected to a transistor which value is VBE. So this is nothing but this is the NPN transistor, so I can term this one as a diode. Okay, so this is nothing but a clamp circuit. So during the positive half cycle, the capacitor gets charged to Vm, and during the negative, so there is no output signal at so there is no output signal during the positive half cycle, but here I have a diode, so it will be at 0.7 volt. During the negative half cycle, the capacitor get discharged, and it get discharged up to 2 Vm. Okay, so minus 2 Vm. So you can see the signal is present during the which is less than 180 degree. Okay, so here the Q point is located here. Okay, here is where the Q point is located, that is below the cutoff region. If it is below, if it is located below the cutoff region, so my input signal is like this. Okay, this is my input signal. So my output, so my output is actually from so my output signal is like this only. So I will get the IC value for less than, this is a train of the pulse signal. Okay, so this train of pulse signal that is which is less than 180 degree. Okay, that is what obtained at the at the collector output. Okay. So when the signal of many frequencies are present at the input of the tuned amplifier, it will select and strongly amplify the signal of the resonant frequency while rejecting the all other frequency. So the pulse is a combination of different sine output. Okay. So sine signal, so it has a different range of frequency, but the tuned amplifier will select the particular frequency. So this signal only we have applied to a this signal only we are applying to a capacitor followed by a inductor. This inductor is having a resistance of R. Okay. So this signal we are applying to the tuned circuit. Okay. And I have a load resistance of RL. Okay. So I can replace the circuit. I can replace the circuit as C, and this is L followed by resistance. This is RP. Okay, RP followed by RL. So whereas this RP is value is Q into XL. Okay, where Q is a quality factor, which is nothing but resonant frequency divided by bandwidth. So the RAC value. So this circuit is again replaced. I am going to replace this RP and RAC. Okay. So what is the value of RAC? RAC is RL in parallel with RP. Okay. So here if the signal is present, here the impedance of the capacitance is very low, and the impedance of the resistance is very high. Therefore the signal will charge the capacitance. Okay. It will charge the capacitance, and during the discharge time this will give a current to this inductance. Therefore you will get a sine output. So if a single current pulse drive this LC circuit, we will get a damped sine wave output. If a train of narrow pulse of the current pulse drive the LC circuit, it will give you will get a undamped sine wave output. So we know that V1 by V2 is equal to N1 by N2, that is equal to I2 by I1. So this V1 I can write it as I1 R1 divided by I2 R2. So I can write instead of I1 by I2 I can write N2 by N1. Okay, so I can write N2 by N1. So therefore R1 I can write as N1 N2 the whole square into R2, where here R1 is a primary resistance and R2 is a secondary resistance. Okay, so the R1 value is N1 by N2 whole square divided by RL. So RL is your secondary resistance. So we know that the PDC value. What is the PDC value? PDC value is VCE saturation into ICC into IDC. Okay, IDC. and we know that the power dissipation, okay, a power dissipation by the transistor is nothing but PD is equal to PDC minus PAC. So what is the value of PAC now? PAC equal to PDC minus PD. Sorry, this is nothing but power dissipation by the transistor. PD, that is when the transistor is on. When the transistor is on, the output is nothing but VCE saturation into IDC. So what is the PDC value? DC power, that is PDC. PDC is nothing but VCC into IDC. Okay. So I can write what is the value of PDC? ICC into IDC minus VCE saturation into IDC. Okay. So we know that the efficiency, conversion efficiency is PAC by PDC into 100. So this is nothing but VCC IDC minus VCE saturation IDC by VCC into IDC. So I can take IDC common. So if I take IDC common and if I divide by VCC, I will get 1 minus VCE saturation by VCC into 100. So we know that the VCE saturation values were less than 0.2. Okay. So this value is nothing but around 5. Okay. So we'll get 2 divided by 50, 1 divided by 25. 1 divided by 25 is 0.04. Okay. So you will get 1 minus 0.04. Okay. So you can see the efficiency is nearly 100%. So this is nothing but maximum conversion efficiency. So here the ZR, I can give it as L divided by CR, and Q we already know that this is FR divided by bandwidth, that is nothing but 2 pi L FR divided by R. So the advantage of this amplifier is it is producing a small power loss, and it is used in the tuned circuit, and it is also used in the RF oscillator amplifiers. Okay, it is used in RF oscillators, amplifiers, FM transmitters. Tuned amplifiers, FM transmitters. Sorry, Disadvantages: it has a very poor linearity, and it is not suitable for audio amplifier. Due to lot of noises, and it is not used for low frequency, since the capacitance and inductors become bulky. Application is not used. And it has a small conduction angle. The impedance of the parallel resonance circuit at resonance is called as dynamic impedance. Okay. So for the parallel resonance circuit, the impedance values are very high. So let us discuss on problem on based on this tuned amplifiers. Consider the circuit. This is 5:1. The Q value of this parallel resonance circuit is more than 10. So they have asked about the find the AC load line, and they have asked about the conversion, maximum conversion efficiency, and PAC value. Okay, so this is what they have asked. So first let us find, so we know that R1, the AC load line, RAC value. So RAC is nothing but N1 by N2 the whole square into RL. So the RL value they have given us 50. So you substitute the value 5 by 1 the whole square into 50. So that is nothing but 25 into 50, that is 1250. So this is your RAC value. So in order to find the PAC is nothing but VM whole square divided by RAC. So VM square divided by 2 into RAC. So VM square is nothing but VCC square divided by 2 RAC. So you substitute the value 50 square divided by 2 into 25 into 50. Okay, so we'll get PAC is equal to 100. Sorry, one. Equal to 1 watt. Next, in order to find the efficiency is nothing but PAC divided by PDC. So we know that in order to get the maximum power efficiency, there is nothing but PAC divided by PD plus PAC. Okay, that is into 100%. So you substitute 1 divided by 1 plus PD into 100. So what is the power dissipation at they are given the power dissipation of the transistor. Okay, they given in the problem itself the power dissipation of the transistor is 4 milliwatt. So you substitute this one, so you will get 1 divided by 1 plus 4 milli into 100. So the conversion efficiency value is 99.6%. So thank you very much.